So before we start, let me just mention that at the moment you can find a link to the DVDs.
You're supposed to find
No, you can find the link, but it doesn't work. But eventually, I hope it will work, and you'll be able to see all these lectures. And so please continue with your third lecture.
So let me Let me start by making a remark which hopefully will clarify certain confusion that we had yesterday, especially regarding Vasily's question about where did the quotient go, even though he's not here. So the statement is follows. So the space of flat connections by the gauge transformation is isomorphic in certain sense to the space of all connections. Is equivalent to the space of all connections mod out by the complexified gauge transformation. So roughly speaking,
so these are connections on the surface? Or
sorry?
These are flat connections on the surface?
Right, yeah. So, okay. So in fact, there's a similar statement when you do a Kähler reduction, which is to say you could...
sorry, I thought that if you take complexified connection quotient by gauge group, you're supposed to roughly get a cotangent bundle of this.
No.
There is a cotangent bundle. How is it missing?
Well, okay. So let me just write. Okay. T of F inverse 0 mod out the tangent direction by the gauge transformation. This the space of all connections. So this is sort of the infinitesimal version of
theorem, right?
Sorry?
That's a Naras-Stefan-Stradlin theorem that you're referring to.
Yeah. So, and then there's a related statement. There's a related statement which is follows. So on the left-hand side, A is the affine space of all connections. L is the pre-quantum line bundle. H0 means I'm taking the holomorphic section. G means I'm going down to the quotient like this. So basically, on the two, and then here it's the same thing, but I'm modding out by the complexified gauge transformation, and this space inherits a Kähler structure, and then I perform the pre-quantization. I find a pre-quantum line bundle, which I call L twiddle. So these two are again equivalent. Obviously, I won't be able to show you how to prove this. So on the two sides of this equation represents two different approaches to quantization. On the left-hand side, what you do is basically you quantize first, then go down to the quotient. On the right is you go down to the quotient first, then quantize. You can see, well, I mean, here you find the line bundle, which is the pre-quantum line bundle, then take the holomorphic section, and then you go down to the quotient by doing this. Here it's the opposite order. So yesterday I said that what I was doing is here, namely I quantize first and then go down to the quotient. But indeed, actually, it wasn't quite correct. What I should be saying is that this is actually what I'm doing. But unfortunately, and up until yesterday, I did not appreciate this subtlety, so there was a bit of confusion here.
So this is like an instance of quantization commuters reduction, right?
I guess you could say so. Now, okay. With that said, let me tell you what I'm going to do today. And so now, if this A were not infinite dimensional space, then that's the end of the story. This guy inherits a Kähler structure, which you can do quantization. But then, in the case this is infinite dimensional, so what happens is that this guy must be supplemented with the determinant line bundle that I introduced yesterday. in order for things to work. You will see in a minute how does that work. And so what I would do is that I'll finish the computation of the determinant line bundle that we did not finish yesterday. And then after that, that's what I'm going to do. And then when this is done, we would be equipped with the knowledge of the wave function, which then, with which we can figure out how does the mapping class group of the torus act on wave functions, and then this will tell us how we perform surgeries, and we can do some concrete calculations. And in the end, I hope to get to the knots. As we have seen, so this is the determinant that we have calculated yesterday. U here, you can just think of it as a number. But for the gauge theory problem, the complex for which we are computing the determinant is followed. So this means that it's complexified and it transforms in the adjoint representation. So let me just for a zero form here, let me call it phi. Of course, I can decompose it. It's written as phi a ta. If ta is the representation matrix of the algebra, then I can decompose it further into those guys living in the Cartan subalgebra plus those guys living not living in the Cartan subalgebra. So I divided the algebra into Cartans and positive roots. And so now different modes, this guy and this guy and this guy, are charged differently under this holonomy. So basically U is that I'm prescribing a fixed holonomy around these two cycles. So the phi h, they have charge 0 under the holonomy, while phi of alpha, their charge is alpha paired with U. Okay, which means when I compute the determinant, I need to really take all of these modes and multiply this factor together. And so just a matter of notation here, I'm writing the determinants as something non-holomorphic times the square of something holomorphic. This guy is holomorphic. Then you just give it a name. It doesn't mean that this doesn't mean that this is a determinant of this operator. I'm just giving it a name for notational convenience. Now, so in the end, we're supposed to just take a so the full determinant should be equal to the product Okay, so to explain this formula, I'm just taking, so remember these guys are charged. These guys are charged. With this. Well, this is the charge under the holonomy. So for each alpha, I got this factor. While for the Cartan subalgebra, they are not charged. So I get a 0 charge here, but raised to the rth power. R is the rank of the group. Now, we did not quite calculate the determinant for 0 charge, namely for 0 holonomy. But what you can do is that you can just sort of carefully take this formula, carefully send U and V, send U to 0. But before you can do that, you have to remove certain modes. That will become 0 modes as you set U to 0. But this is a useful trick to do this calculation. Anyway, I don't want to go there.
Excuse me, the equivalence module specified connections are equivalent to all connections modulo complex validation. So on the right, do we have the module specific homomorphic equivalent? So it's not the right hand side of the equivalence.
Do we have what?
what is right hand side of the equivalence? All connections modulo complexified gauge transformation.
Right.
Is it the same as modular space of holomorphic G bundles?
Right. Actually, yeah, it's the it's the modular space of. Actually, in the paper I refer to modular space of Cauchy-Riemann operators. So basically, B bar operators of B bar operators on a vector bundle.
I think they're probably neglecting some kind of stability issues, right?
Yeah,
That's
yeah.
Just yesterday we had discussion how the module space of flat connections for compact group is related to the module space of holomorphic G bundles.
Right.
And you say it's just the same.
This is the correspondence. But yesterday I did not mention this because I didn't know this.
So they are the same spaces.
Right. In certain, because this guy is understood as some sort of differential manifold, but this guy is understood as an algebraic variety. So I don't know exactly how, in what sense is this correspondence meaningful, but okay. So that's the point that I failed to appreciate up until yesterday.
But then what Raimundo suggested yesterday applies. You consider the one bundle over 1G, take the determinant.
Right, the determinant of the canonical bundle over the bundle, whatever.
Yeah.
That I have no clue. Okay. So where was I? Okay. So I hope this is clear, right? And then in particular, let's get what is the metric. Remember, this term is the metric, and this will actually answer your question: where does H come from? Okay, so well, let's do this. The metric is this. So for each alpha, you get this term. Because you only get this for 6 sum over alpha greater than 0. These guys are not charged, so you don't get this factor. I'm just taking the product of these guys for all the modes with alpha greater than 0. That's squared. But this is just equal to so you get an H here. And that's what quite simple-minded as to how H comes from. I have no idea how to understand this from Raymond's point of view. Okay, so, and then now another remark is what exactly is this product? This is something that I just have to quote by using the McDonald thing. This is actually the antisymmetric Weyl function at level h with parameter tau and u. And then let me just give you the formula for general theta. So this is the formula for general theta. While theta minus meaning you want this guy to be antisymmetric under the Weyl group, which means you just do this sum over all the, well, you use the method of images to make it antisymmetric, or if you remove this factor, it becomes symmetric. But, yeah. So just to show you that this actually makes sense, what you can do is so you just take this formula and then set Q to 0. Then what you get on both sides will be the following. So by setting Q to 0 in this formula, what you get is this guy. While in this product formula, by setting Q to 0, what you get is this product. Well, this is the Weyl denominator formula. So this guy, the McDonald identity is just sort of the generalization of this in case of affine algebra. Okay.
Jan, I'm sorry. Oh, I'm surprised that you get H and not H check. So is this number H? What's the definition of H? Is the eigenvalue of the Casimir operator?
For me, my understanding of this is very simple. So just take the trace of take the trace in the adjoint representation.
Yes.
Or something. It's the equivalent to take the trace in the fundamental, but with an H here. That's my working definition of H.
So the conceptual number is the same as a Casimirian adjoint, right?
Right, but that's why I'm surprised that it's H and not H check. Are your groups simply laced?
Yes.
Oh, okay.
So okay, is there
Then there's the
something
same number, yeah.
Okay.
But I think H check is in general there.
Well, you have to receive the simple list, please.
Because eventually I want to, in later manipulation, I need to, when I work out the S2, I need to replace the summation over the root lattice to the dual lattice, and I think if the group is not simply laced, you can't simply do that. Okay, so this is the this is the end of the determinant line bundle. But again, as I said, so the naive pre-quantization of this space using the inherited Kähler structure must be supplemented by this determinant line bundle in order for things to work. And then, so let me just make a brief remark of the role of this determinant line bundle. So what happens basically is that, so when you do this quotient, what you're saying is that you take any connection and then you write it as the gauge transformation of a constant gauge field with prescribed holonomy. You write it as the gauge transformation of that particular prescribed gauge field, which means you're sort of doing a change of variable. You're changing from using connection as your variable to using the group, the gauge group, as your variable. In this case, you get a measure factor, which happens to be the determinant line bundle, and also another role that's played by this determinant line bundle is such that it enables you to be able to identify the Hilbert space on with two different complex structures. So it allows you to move in the space of complex structures and still be able to identify them. So this is the twofold role of this determinant line bundle. Now, I still haven't told you how to. Okay, the simple mind. Okay. Now, this guy said it inherits a symplectic structure which is pretty simple. It's just omega is equal to k times. It's the thing I wrote yesterday. Delta U1, delta U2. U1, U2 are here. Well, again, I can write it as minus I k tau to delta U, delta U r. Now, the quantization of this guy is, again, since they are also defined up to translation in the root lattice, so the quantization of this guy is exactly the same as what we did in the toy model. And then the analogy is that you replace, okay, in this toy model, you replace the integer lattice to the weight lattice here, and then you replace, integer lattice to the root lattice, and then the integer lattice divided by k to the weight lattice divided by k. So again, by just applying this guy and understanding this this correspondence, what you get is in fact, I don't need to write it. What you get is exactly theta so the summation of n, which is in the integer lattice, is replaced now with summation in the root lattice. and then integer divided by k is now weight. Well, this is just theta, the theta function at gamma and level k. Now, there's an extra condition, that is I have to mod out to the residual gauge symmetry, which is a Weyl group, which means I need to require this guy to be invariant to the Weyl group, which this condition is not there in this case, but I need to impose this. Now, what's the periodicity of this function? It's given by that. Well, so it's periodic if you shift by an integer, but if you shift in this direction, it picks up an extra phase. I don't know what I'm writing in my notes, but yeah, okay. I think I made a mistake in my notes, so now I have no idea what was this. I think it might be something like the gamma squared or something, like k squared, something. I have no idea now. Sorry. Okay, so. Now, what is left to be done is that we need to figure out what is the wave function. Given that the time is not really on my side, so let me just say that okay, we can take the cue from the fact that our metric is actually the metric. The metric for the line bundle is actually e to the what was that? H plus k u squared. So you would have guessed that the wave function is actually the theta function at level k plus h. Okay, and then we know that it will have to be antisymmetric, because antisymmetric under the Weyl group, because we know that its product with this guy has to be symmetric, because this guy is symmetric. So in the end, let me just give you the answer. So the holomorphic section is this guy. So it's the antisymmetric theta function at level k plus h with this weight, and now it's easy to show that this has the correct well. And then what is more common? What makes sense to do now is that we can associate, we can divide this guy by this thing, which means I just divide it just because I can do that, and then I define this to be my wave function, and then I just associate this holomorphic function. I just put this together with the metric, because I can always shift the metric by the product of a holomorphic function and an anti-holomorphic function. That's just Taylor gauge transformation. So I'm just going to use this as my wave function, and then you can recognize this as actually the character for the representation of the FMD algebra. So this, by the way, is how actually the McDonald identity is derived. Basically, you look at the denominator and the numerator and denominator, and then you go to the trivial representation, which is set gamma to 0, and then you'll find that, well, that's exactly how Weyl denominator formula is derived too. So, questions?
Yeah. So you said something yesterday that is the shift in k, the h,
Right.
that come in. You said that it was related to the norm.
Right. Yes. So
what symmetry are you breaking there?
well, it's basically the tension between gauge invariance and the holomorphicity.
But usually when you, I mean, at least what I'm used to, usually when you say an anomaly, you have a classical symmetry that you break on the quantum level. So what symmetry are you breaking? And you call it an anomaly. I can see that it comes from the determinants. It's like in one loop or whatever, I don't know.
Well, I guess, yeah, I guess if you look at how Fujikawa derived his anomaly formula from looking at the determinant factor, I guess this is a similar process, even though I can't really tell you which symmetry was being broken by quantum corrections. So now we have found out.
Isn't psi gamma k? Is it exactly character, or it's character multiplied by something?
That's the exact character.
It's the character for what module?
For the representation of f on the algebra at level k and gamma and weight gamma. Okay. So, and the gammas are different. I mean, are orthogonal for different gammas under the metric this times the theta minus over there. So now we have found out what is the wave function. We can try to proceed to figure out what is the modular property of the wave functions, and that's going to lead us to the S and T. So if you choose, okay. So the mapping class group of torus is just SL to Z. It's generated by T and S. So what T does is that I'm identifying this case with this case. So what T does is that it introduces an extra twist. And what S does is that it swaps A cycles and B cycles, namely T. Under T, tau goes to tau plus 1, and under S, tau goes to minus 1 over tau. Okay, now, since, yeah, okay. So, well, just by looking at the expression of the theta function, it's pretty easy to see that under shifted by tau, the theta function only changed by a phase. Let me just give you the answer. So, under shift tau to tau plus 1, the theta function just changes by a phase. Now, since the character is a ratio of two theta functions, I just get the tau matrix acting on those two. So this phase comes from the denominator, numerator. This phase comes from the denominator. Now, this phase can be written in a quite interesting way. Okay, I've split this into the second Casimir of the representation labeled by the weight gamma plus the central charge term. Central charge is given by this, which is the central charge for the Western mean elevation model. Okay, this is the T matrix. S matrix. S matrix requires some more work, but now let me just walk you through how you do that. Sorry. Yes. Okay, so since I said that S takes tau to minus 1 over tau, but then you want to reinstate it into the numerator, right? And what you do is then that you apply Poisson resummation. And then in this process, the Poisson resummation turns the summation over the root lattice to the dual of the root lattice, which is the weight lattice. Then you again break the summation over the weight lattice you break it into summation over weight lattice divided by k times, or in this case, k plus h times the root lattice. And then basically what you do is you break the summation of the weight lattice into the fundamental region of the affine Weyl group. Okay, so you sum first over the fundamental region of the affine Weyl group is called, I think, called Weyl alcove, and so which means you sum in the alcove first, and then sum over the image of the affine Weyl group. So let me.
In your formula for theta function, that one just in the middle of the blackboard, you have the summation over alpha in lambda equals theta function. Where is the in the first line? Where is u?
U is sorry. Sorry.
Just there?
Yeah, that's the only place.
Okay, thank you.
Yeah. Well, by the way, since tau has always positive imaginary part, so this term serves to converge the whole series the summation. And also, one thing you can check is that theta has this periodicity condition, what's by definition true. So you can shift the weight by k times the root, you get it back, because if you shift gamma by k times the root, you get a root, and then you can just reabsorb this into the summation of the root lattice. So you get whatever you get. Now, let me just quote the formula, because I do want to do some concrete calculation. So S alpha beta, so alpha beta are the two weights. Yeah, that's the formula. So let me just comment. L here is the number of simple roots, and G is the dimension of the group. R is the rank of the group. So this factor is basically the number of positive roots. Now this factor comes from doing the Poisson summation. When you go over from the root lattice to weight lattice, you get the ratio of the volume factor. But this is whatever's left. Now, to be concrete, let's go to SU2. Work out this formula. Now, slightly more general maybe. So for SUN, you pick up, so let's figure out what is the root lattice and what is the weight lattice. So let me pick a n-dimensional Euclidean space. Then the roots are follows. So these are the positive roots if the 1 precedes the -1, otherwise it's negative. And then, for example, the weight for the fundamental is, this is the weight for the fundamental representation. And the Weyl vector, which is half of the sum of all the positive roots, is going to be specifies SU2. So, well, there's only one root, which is 1 minus 1. And, oh, by the way, in SU2, the Weyl reflection just flips the two entries. And then this, never mind. And then for sigma half representation, the weight is, of course, just a half 1 minus 1. So let me just figure out, well, for thing. So let's just use that to figure out what is this, and then we are ready to do some real calculation. Well, let me just, so I'm taking spin a half A, spin a half B. You know, it's a bit unfortunate, the spins are labeled by half integers, so now let's work out each factor there. That's silent here. Do you have questions? Okay, you can recognize each factor's, well, dimension of the group is 3 and so forth. These factors are pretty trivial. And then now, as I said, the Weyl reflection flips one with -1. That's why you get complex conjugation here. And then here it's A plus 1 because I'm shifting this weight by the root, by the Weyl roots, by the Weyl vector. Okay, if you put everything together, the following formula. This guy goes into a sign here. So an exercise for you. Is to show that SAB actually is orthogonal. Okay. So here is the formula, and let me also quote what is T here. T is diagonal because T only shifts stuff by a phase. It's equal to we know that's right. Oh, okay. In fact, for T, I only need a spin a half. I don't need anything more than that. So it's okay. So we can now do some calculation.
So in the top there, so your A, B rounds over plus and minus 1?
No, they are spin 0, spin 0, a half, 1, 2, etc., etc. One important thing that I need to mention is that for a fixed level, the spin something like that.
K over 2.
K over 2.
I think that should.
So I think I should get exactly K state. I should exactly get K plus 1 states, right? K plus 1 states. Okay. So let's do some calculation. Any questions so far? Coming back to the first lecture, we showed that sphere can be written as gluing of two solid tori, except there's an S in between, so you don't glue them back to back, but you glue them after twisting. Okay, now this will tell me that the partition function. By the way, how do you describe these states labeled by different weights? You can just think of it as inserting a Wilson line in the middle, transforming in the corresponding representation. Now, since I want to compute this partition function of S3, that means I need to insert actually. That means I don't want to have any Wilson lines in between. Namely, I just insert the trivial. I mean, Wilson lines transforming the trivial representation spin 0 and spin 0, and that by definition is just going to be S00, the matrix element of S2, but two entries are in spin 0. Okay. What is that? Well, it's that. So Q is K plus 2. Now, I also would like to compute S3 but with the Wilson line, let's say transforming in spin and a half representation. Then what I do is quite simple. I just
Sorry, what about the three-factor?
sorry.
What about the three-factor? The square root of 2 over k plus 2? Did you drop it? Because you said it is 0, 0, but it has a three-factor.
Yeah, I think you're right.
You cannot drop it.
Right, yeah, you're absolutely. Actually, there's a very important comment I need to make. Sorry. So we just see that in the large k limit goes to k to the minus 3 halves, right? Because you got 1 over k here and 1 over k square root there. So in general, if you do perturbation theory, the large k behavior goes like k to the minus a half the dimension of G. So in doing perturbation theory, of course, what you do is you pick a flat connection and you do a Gaussian integral around that. So dA is exactly the differential with twisted by the flat connection. You need to compute these groups. But for S3, there's no non-trivial flat connection, so these guys go back to the RAM. And there's no this guy either. This is one-dimensional, this is 3. So you get k to the... Okay, this is the general large k behavior for... sorry. Okay.
So write the factor, I mean, 1 square root of, right, you didn't write it down.
Yeah. Which I think there might be a factor of half something. Anyway, it is pretty elementary. Now, if I want to compute S3 with a Wilson loop in it, transforming in representation spin and a half, then what I do is I simply put a spin and a half line here. Again, apply the S view. So what I get in the end is that, well, in this case I need to S plus Wilson loop. I need to normalize everybody according to this. What I get is this sign. In this case, it's k plus 2. K plus 2. That's a pi. Right. So in the end, this time I no, this time there is no prefactors anymore, and it's a plus because I feel like it's you get a cosine, and yeah. Okay. And we can also do a Hopf link, and I will do a Hopf link by using this direct method, and then also later I will get using surgery to get the scaling relations for the Jones polynomial, and I can check both sides, see if they agree. Well, the Hopf link think it's just a repetition of the same story. Off link. Let me just, for simplicity, say that the transform is in a half. Then, well, what I get is just S. Okay. And I don't think I want to write down what's the answer. It's pretty simple. So far is the direct computation. Next, I need to go to knots. What's this? Oh, so good.
I have a question. The fact that the ratio of those theta functions is a character of representation for finite algebra, should it follow from what you have presented here, or it's just a parallel fact that you...
Yes, there's a very clever way of understanding it. I think what due to Linda, so he realized that the S matrix, the S2 matrix diagonalizes the fusion root, right? Okay, so if you apply S matrix, well, if you diagonalize the fusion root, that means you are looking for something that composes diagonally under. So
I'm just trying to ask if you have explained that and I didn't understand, or you just didn't explain.
I didn't.
Okay, so it's just a fact.
Right.
Okay.
So this was the example that I was about to give at the end of the first lecture, but then I want to abide by the time limit, so I didn't do it. So let me okay, knots. So let me just make a brief remark of why Buchan-Simon theory even give you anything meaningful about knot invariance. Well, the answer is very simple. The expectation value of a Wilson loop inside Buchan-Simon theory is independent, is invariant if you deform the knot, which means by definition it's a knot invariant. Okay. Yeah. Okay. So I again need to. Okay, let me just tell you what you're supposed to do. So Kaufman realized that a knot invariant can be uniquely fixed by following string relations. Namely, if in the vicinity of a crossing you have you have these three crossings, and the string relation tells us that these three are somehow related. This data, that's the normalization of the trivial knot, but uniquely fixed what's the knot polynomial for you. So this is what's realized by Kaufman, and so we can use try to figure out how do we find. Well, we know how to compute these guys, right? We just did it there. We need to figure out how to get the string relations. So what you're supposed to be doing is the following. So you have a crossing, so you just cut that thing out. What you get, of course, on the boundary is just S2 with 4 punctures. Now, you're supposed to just study the composition on this Riemann surface with punctures and figure out how does the mapping class group act on a Hilbert space. And then you can, okay, the Hilbert, the modular space of this guy with 4 punctures is 2-dimensional. It's basically the cross ratio of the position of the 4 points, so it's one complex number. So once you figure out how the mapping class group act on Hilbert space, now you can just ask, how do you relate these two? And how do you relate it is given by, it's a name that I don't know how to pronounce. This connection. This connection helps you to identify the Hilbert space as you move along the moduli space of the Riemann surface with punctures. And but here we obviously are not going to do this. So let's just try to stretch our existing knowledge and try to figure out the problem anyway. So we have a similar problem. when we have a torus, and let's put two Wilson lines in it, transforming alpha and we know how to twist it, right? Because twisting is just, we apply the T matrix, right? So twisting, apply the T, you give them one twist, right? And then we know how does well, we know the formula for T matrix, which I erased. Okay, it's here. So this is how T matrix acts. So now here there's going to be a bit of hand waving here. So for two Wilson lines, again I can expand it in terms of Wilson lines transforming. I can spin 0 as a direct sum with spin 1. This is provided k is greater than or equal to 2. So if in case k is equal to 1, then this guy is not allowed. Which means, and also, let me also comment on this this factor, central charge term. So the central charge term is there even when there's no Wilson line in it, which means it's an intrinsic property of the three manifold. In fact, here I identify this term as the related to the framing of the three manifold. But here, since we're just doing knots, we don't need to care about this term, so then we can ignore it. Okay, now, so we know that spin 0 and spin 1, each term, they respond differently to this T matrix. They pick up different phase factors, right? So let me just write down the phase factor that they will pick up. So for the spin 0, this line will pick up yeah, okay. So this is for 2 pi twisting. This is for 2 pi twisting. We don't know how to, for the, using our existing knowledge, we don't know how to do pi twisting. But I suppose dividing the answer by 2 is not a bad idea. So these factors is just the difference between the Casimir of this representation to the, and then the Casimir of the two representations here. Okay, so let me draw some diagrams. Again, I have a undercrossing. So the reason I call it B is because it's actually the braiding operation. So, for example, the first Jones polynomial was found by just studying the representation of the braid group. Well, it was Kaufman come a bit later. So now we know that this braiding matrix has got two eigenvalues. One is this, the other is that. But there's a further twist, which is to say, actually I need extra minus sign here. The reason is because I have two spin and a half representations. I'm combining them to spin 0, so actually the combination is antisymmetric. So when I swap the two, I got an extra sign, which means B in a basis has got this form. Okay. Now, next I just need to use the Cayley-Hamilton theorem, which says that any matrix satisfies its own characteristic equation, namely T to the n minus trace of T n minus 1, all the way to the determinant of t is equal to 0. So if you replace t with its eigenvalue, if this is just its characteristic equation, but the matrix itself satisfies the same equation, which means B satisfies the following. B squared minus this is the sum of these two guys. This is the determinant. Okay, since I know that applying B once I get this one, applying B twice I get that one, that tells me I got the following relation. And this is the relation that we're seeking here. So the three numbers are given by these numbers. But this is not the Jones polynomial yet. Okay, I'm going to do that now. The reason is that here, this polynomial, this is a valid knot polynomial, but it still is sensitive to the framing of the knot. We'll see why. Now let's just do some calculation and then compare with the explicit calculation that we did a moment ago. Let me just do this knot, do this hot link. So I'm going to, in this undercrossing, I'm going to swap it into L0 and an upper crossing. So this is what happens when I apply the braiding once. So these two becomes like that, but with a factor. What's the factor? Hold on. Half. So if I apply the braiding twice, I completely untie this link, so I get this factor. Now, actually, all of the diagrams are known, right? We know what's the expectation value of a trivial Wilson loop, and 2 times this is square of that. We know this, we computed it. The answer is, so this is this one. And this is it's a square because I've got 2 of these. Now this one's slightly tricky. See, this almost is a trivial link. The only difference is that if I straighten this component, I introduce an extra, I think it's a right-handed twist, I believe. No, left-handed twist. So if I straighten this one out, I mean, if this were a strand of finite thickness, then I got the twisting. And we know that how the twisting, which is given by the Casimir of spin a half, which is 3/4, which means for this, it's equal to that times. Now, we can show that, this is indeed an equality, except this knot polynomial does know about the self-linking, the twisting of the knot. The Jones polynomial, however, is insensitive to that. So how do we get there? We just need to somehow build in, or rather remove, the information of twisting from the skein relation. Now we know that, so from here to here, we just apply one twist, but coming with this one twist, half twist rather. So coming with this half twist, each strand gets a half twist, which means you get one twist, and which means I just need to remove this extra factor of q to the minus 3/4 from this term, and also because this guy I get twice as much. I mean the square of this guy. So if I remove these factors from this scaling relation, what I'll get is and this is exactly the scaling relation for the Jones polynomial. And yeah, punctuality. Okay, I'm done.
Thank you very much for this and the other lectures. Any comments, questions?
Yeah.
Just so from this lecture, I understood that wave functions of Chern-Simons level K are labeled by representation of affine Kac-Moody level K, and the wave function's character in that representation. So, but you have explicit formulas for that, and the relation can be understood without confusing actually, right? The wave function. Just what is the physical explanation for this fact? The wave function of Chern-Simons is a character of central extended loop group. There must be a simple physical picture.
Yeah, the simple physical picture, I guess, the closest you can get is by applying Valinda's reasoning. He basically says, let me just, okay, since this is question time, right, I can go all the time without any limit.
Not so sure.
So, you have representation I, tensor product representation J. The fusion is going to, I don't like this. So this is the fusion coefficient, right? And then we know if you think of the fusion coefficient as a matrix labeled by I, namely you write it like this. And then Valinda showed that if you apply S here, S here, this is diagonal. Let me call it DI. So DI is diagonal. And then the eigenvalue, so lambda I1, lambda I2, whatever it is actually, well, this is equal to S I1, Si0, I believe. I think I remember this. Okay, this factor looks a bit suspicious to me, but I might have remembered it wrong. Which means to figure out what's the S matrix, you just need to figure out what's the eigenvalue for the fusion coefficient, right? And then if there's one thing that fuses diagonally, that's the character. Right? And
You might explain some property, but it's not what I'm asking. I'm asking a simple physical picture, which you draw like a circle, and like one path integral equals another path integral.
What about the original Wittgen's
Right, about
who was saying that the Chern-Simons theory with boundary is not gauge invariant, and to cancel this anomaly, you need to add something like a W is a W, say curve.
Yeah, something like that. I just want a reminder how it works.
But I think the simplest reason is the following. You have to solve the Gauss law for Chern-Simons, right? If you do, canonical quantization. And the simplest way to present Gauss law solution, you can write just Verzumina-Witten model coupled to, your gauge potential. And this will solve you exactly, this Gauss law, and this has interpretation as conformal block of Verzumina-Witten model. So that's basically the simplest heuristic argument.
So I guess probably then just spelling out the Witten's idea in a more precise form, right? That this W is a W sitting at the boundary.
Right. I mean, his argument is heuristic. I mean, it's not really.
Yeah, but I think I wanted heuristic argument.
Yeah, it's
So we have a character in representation
representation that the vector space and character of that representation taking trace of operator in the Hilbert space. So what is the physical meaning of that Hilbert space? That space of states in the representation.
Okay. For the torus with for the torus with this guy, it's this. You do a solid torus, you put a Wilson line in it, and transforming in gamma, and you perform the path integral with this guy in it. That's going to give you a vector inside of this sigma. But this vector corresponds to this vector.
So you take torus and
Take a solid torus.
solid torus.
Do a transformation, path integral transformation theory with the Wilson line in it.
In it.
With, this is a solid torus.
And like in the center of solid torus, you put a circle which goes.
No, you just put this Wilson line in it.
You have a and you have a boundary of that solid torus. Right?
Yes.
Which
Because
is
so
torus, okay?
a boundary of solid torus.
Yes, you do class integral there and you get a vector.
Vector in the Hilbert space that I assign to the torus. Okay.
Oh no, sorry, the Hilbert space was finite dimensional, the space of.
Right.
No, I'm not asking about that space. I'm asking about Hilbert space representation at level K. It was
I don't think I understand your question.
There's probably the Hilbert space of this Carol WZW, which leads to the boundary.
so your wave function is a character of affine Lie algebra.
Right.
It's a character in certain representation.
Right.
That representation is a highest weight module,
Right.
and it's infinite dimensional. Is it correct?
No, it's
It's not.
No, yeah.
It's
Uh,
infinite dimensional.
in this case, we're only taking the integral representations. That's why for SU2 we only get
It's integrable representation, but this
These are finite dimensional.
Yeah, very much infinite-dimensional.
the highest weight representation.
Yeah, but I think the answer, yeah, it's simple, but the answer to your question is that why do you want a physical interpretation for this space?
because the
No, the answer is that it's a conformal block for the Besemino-Witten on the torus, right? And these conformal blocks are computed as traces in some representations.
Very good. So my question is, it's a trace in some representation of an operator. In quantum mechanics, we know that we take a trace of we get a trace of an operator when we have a Hilbert space when our operator asks on that Hilbert space. So that representation is itself a Hilbert space for some quantum mechanical problem. And I'm asking, what is the quantum mechanical
So
problem?
I think Anthony is replacing is
Right,
answering
so-
that. It's the Besemino-Witten, right? It's a Carol Besemino-Witten, and then
So
you.
the Hilbert space of the Carol WZW living on the boundary. Boundary is just this torus. So I think that's probably, well, I don't know, one should, probably your question is even more precise, so, but there maybe one should really look how it goes, but certainly that's the direction in which the answer goes. So you have the Chern-Simons in the bulk, you have the WZW on the boundary, the WZW has an infinite dimensional Hilbert space, and this character is a trace over this Hilbert space.
Right, but when then I ask him, so it's an operator, it's a character, it's a trace in Hilbert space, there should be quantum mechanics. Quantum mechanics, it means one-dimensional field theory.
No, okay, you can interpret one of the directions of the torus as time.
Okay,
So then you want an infinite, it's an infinite dimensional system. So
I think I got it. So the other circle you treat it as a loop group, right? On the other circle you have a circle, you have a function on circle valued in the Lie algebra of the group. So it's like so this is a quantization of loop group.
No, you can say so, yeah, or in orbit or in model of a loop group. Say a particular orbit, I would say.
Yeah, I think I got it. Okay, thank you.
Just
Thank you.
think about Adilin and Simons. This is easy.
If there are no more questions, let's thank you once more.